Hello Internet, welcome back to our Voxel terrain. In this video we are going to be focusing on actually tearing up our Quadtree. We're going to be replacing it with a array-based system, and the reason for that is it was pointed out to me that this may not be the best approach because what we've effectively created is a linked tree. And so what that means is each of the subnodes is a reference, or each of the nodes holds a reference to the subnodes, and those can be spread out anywhere in memory. And as our game progresses and gets more advanced, they're going to get spread out further and further in memory as it tries to find places to put them. The problem with that is it sort of breaks our caching solution. So there's a number of caches in your CPU and in your computer. And so there's only limited space to store each of those in, and the further back in your caches you get, the slower accessing that memory gets. So the best way to do this is to store everything as closely together as you can if you're going to be accessing it at one time. We're not doing that here, and part of the reason is our sparse tree where we create and delete things. Because of that, when we create or when we delete something, we could create it at like the end of memory, and then if we have our tree initially at the front, there's a big space there, so we need to load those two things. There's a very low probability that they will be on the same page, and therefore you won't find them. The example I give is like a book. So if you picture the current loaded memory, like all the text on a page of a book, the story crosses multiple pages, and that's sort of your entire project, your entire game. The goal is to get all of your stuff into a little paragraph so that you can fit it all on one page, and that the person doesn't have to flip pages to find what they're looking for. Unfortunately, this solution doesn't do that. It kind of spreads it all over the place. It's like if every single page had footnotes pointing it, or it's a choose your own adventure, which isn't great. So the solution to that is sort of a heap style. So if you're not familiar with a heap, the idea is you have your first node at the first index in your array, and then the next two nodes after that, and you effectively build a binary tree. So the first node is going to be the root node, and then the next two are going to be right directly below that, and then the next four are their children, and so forth. We're going to do the same structure to build a quad tree, but we're going to have 4. So it's going to be a 1, 4, 16, etc. And that should build us our full tree, I think. So that's what we're going to be working on. We're not going to add any new features, but this will set us up so that we can add our marching squares easily. So the marching squares relies on being able to access 4 adjacent nodes and kind of using those as the edges. And so to get all of that working, we need a quick and fast way to do lookups on adjacent nodes. So I can look at this and say, or here and say, what are the 4 nodes adjacent to this intersection here? And I can see there's like 4 grounds and then an empty space. Being able to do that requires us to do a lot of work actually to get this working with our current solution. If we start doing that with our array, that becomes a constant lookup, which is much better. We can do that really fast. So that's sort of our goal. How far we'll get, I don't know. Okay, so I've talked way too long. Let's actually get started. I'm pulling everything apart. Am I doing? Oh God. So what I've done before this is I pulled out our quad tree and actually turned it into a linked quad tree. We're going with the same naming style as C# array or lists have. So the standard list in C# is going to be an array list, and then you have a linked list, and that's just the same structure. It's just linked. So if you're familiar with those two data structures, that's what you get. Here we have our standard linked quad tree, and then we have our other quad tree there. Both of these could potentially be useful, so I'm not going to delete the linked one. Depending on what your project is, it may actually be an appropriate solution. It just isn't for what we're trying to do here. So they're both there. Eventually we'll probably pull those into an interface, but not yet. So what we need to do here is we need to create an array of nodes. And so most of what we're going to be doing is we're going to be pulling all of our logic out of our nodes and moving it into our Quadtree itself. And then the nodes are just going to store data. They're not really going to, they're going to be data objects. They're not going to do anything fancy. So what I'm doing here is I'm creating our array. The array is actually going to store our entire Quadtree. So we're getting rid of the idea of a sparse Quadtree. We're going to create it all at startup, and then we're going to work from there. The other thing I'm going to do is I'm going to change this to a struct. So our Quadtree node is now a struct. The difference here is a struct is a value type. A class is a reference type. So the important bit, the reason this matters is with value types, they're all the information is right there. So effectively, when we create that array, when we create it with structs, we're creating an array that is the size of our struct times the length of our array. That's how much memory we're allocating. So we'll just take a huge chunk and throw it there. If we use classes, what ends up happening is when you create this array, it would be an array of pointers or references to each of those objects, and those objects could be spread everywhere. This should fix that. I'm not 100% familiar with the way C# handles structs. I do know their value types, and I believe it should all be stored in one contiguous block. But whether or not that's true, we'll have to find out. I'm going to remove the subnodes bit because we don't need that anymore. Also, we've got the depth here. We're going to want that. We've got our data, our size, and our position. So all of that we can keep. This bit, I'm going to delete the original subdivide. We don't need that anymore. And then our circle subdivide, I'm going to keep and pull out. Whoa, what is going on? It wasn't letting me scroll. What the heck? That was weird. I'm still using Visual Studio 2015, so that I wouldn't expect that. I have them both installed, so I was maybe using the other one, but that's not the case. So this won't work yet, but we're getting there. What we need to do is actually hook these up so that they will work from our Quadtree. Our Quadtree, again, is going to be doing all of our logic. So isLeaf, that check can also be taken out because all that check is going to do is look at the depth, and I'm not sure we need to store this. I'm going to, because why not? But I think we might be able to pull that out as well, because we can actually get that using logarithms. And I'll talk through that in a bit. The eventual formula is going to be something like the log of the index divided by log 4. So this is log base 4 of I, which is saying more or less what is 4 to the power of what is going to equal this. And in this sort of thing, we actually want the floor of this. So I'll just leave this here. But eventually, this is going to tell us the depth of our thing. One of the things we are going to need to change is we're going to need to take our depth and actually flip it. Previously, we'd actually count down. So the higher the depth was, the closer to the root it was. And then as it got lower and lower, if it was 0, that was a leaf node. We're flipping that. So 0 is our root, and then going down, we get closer and closer to our maximum depth, closer to our leaf nodes. So we'll actually have to do a check based on the depth of the tree. in order to determine if it's a leaf node or not. Get root. Why do we need this? Where is this being used? Let me see. I totally forget. Find all references. Oh, it's just for drawing it. We can keep that, sure. I don't really want to though, so no. So that's going away. We may lose some gizmo drawing right away, but we can fix that. For this, we get our leaf nodes, and this is actually going to be a formula that I'm not going to do yet. For now, we're just going to pass in everything. Keep in mind that is very wrong. The hard part is going to be our subdivide, which isn't going to be a subdivision anymore. It's actually going to be a search. We're actually going to be looking to find nodes that match a specific thing, and then probably return them in this list, and then use that list to actually build something. So we'd return the list, and then we'd set them in here. I think that's how we do it. That seems like the only thing that makes sense. What else do we need? We need to actually build our tree. So right now we have our nodes. We're going to set this equal to a new Quadtree. That's not what I want. What I do want is first, we're going to make that read-onlys just so we can't override the values inside of our Quadtree. And then we've got our nodes, all of that. We're just going to do a build Quadtree with a depth that we're going to pass in. And that should be all the information we need. That's actually wrong because we need to set the position and the size of it because those we don't want to change afterwards. So make a private void. We'll build our Quadtree. And then all we just need to pass in those values again. So float, the size, and then our depth as well. And so the first thing we need to do is actually calculate the tree size. There's some fancy math you can do with binary trees. I believe it's just 2 to the depth minus 1. That doesn't actually work here, at least not that I could see, because if you have a depth of 3, you'll have 21 nodes because you have 1 plus 4 plus 16. And that doesn't equal 64 minus 1. So unless I'm doing that math wrong, I don't think you can do any fancy math for this, so we're just going to do a sum. So I'm just going to calculate the length for int I is 0 to 1, or to the depth. So what we'd be doing, what am I doing? Okay, so the idea here is we're going to increment over this, and then we're going to count the length. So every step down is a subdivision. So what this means is at height or at depth 0, there's only one node. At depth 1, there's 4 nodes because the 1 node got subdivided into 4. Depth 2, it gets divided into 16, and so forth. So 1 plus 4 plus 16, 21. That's what we're doing here. If we pass in 3, we want 1 plus 4 plus 16. So the length plus equals the power. I'm not too concerned about performance here because this is only going to happen once. It's only going to happen when you create this Quadtree. So for now, I'm not that concerned with it. I'm more concerned about all of the things that are happening continuously. So this should get us the length of our tree. And then we just need to return, if I could get this right, there we go. a Quadtree node of t-type, and we'll make that an array. So we just need to return a new array of nodes, and we need to put in length nodes. So we'll make it length long, and that should be good. That should get us our total number of nodes. Yeah, so we have an empty tree now with all of that. The next thing we actually need to do is figure out where all of those are positioned, which we could actually use our subdivide to do that. We could just drill down that way. And maybe that's a good way to do it, but it doesn't seem like a good way to do it. Yeah. So instead, let's build our tree here. This might get a bit gross. What can we do? I think we want to start by saying we want to initialize this. So we want the first node in our tree, like that. And it's going to have a position, a size. It's going to be at depth 0. And then t-type, value, default. Yeah, we'll just keep it at the default value for now. So they'll be uninitialized, they won't have any value, but we're just going to spin it up this way. And then I think we can do recursion here. I don't really want to do recursion here, but it seems like it'd actually be an alright idea. So yeah, let's so we're gonna write a subdivide function. I know I deleted it, but this is gonna be a lot less than the last one. So we pass in the depth we want, and we pass in everything else. I'm also going to pass in, how do I want to do this? The current index, or the index that we want to start at? We can calculate, so I think we want the index we want to create at, and I'll talk about that a little bit. So, this is gross. What we're doing is we're creating a tree, and so to create that tree, we need to actually, no, this is silly. What am I doing? We're just going to do a for and I 0. We can actually start at 1. We can start at 1, and we'll be what we're going to do is we're going to look backwards in our tree. It has been a long time since I've written a heap, so this may not go smoothly. Well, screw it, we're going to try anyway. So if I end up down a creek without a paddle, or, you know, anything, then sorry. Yeah, we'll see. I'm kind of making it up as I go, and that never turns out well. So what we're going to do is we're going to iterate over every element in our array except our initial one, because that one we're seeding the initial value. Then what we're going to do is we're going to, at each index, we're going to actually look backwards and figure out where we were at the last one. We can calculate the depth with that formula I pointed out somewhere. Whatever, it's fine. The current depth is going to be equal to sorry about that. Current depth is going to be equal to the floor of the log of we're gonna do log 10. Sorry, I'm doing log 10 just because I know how that works. So log base 10 of I divided by the log base 10 of 4. So logarithms, if you divide them and they have the same base, it actually becomes the divisor becomes your base, and it's just over I. So how this is working is we're actually, well, this doesn't look like it, we're actually taking the log base 4 of I. And so that should, let's see, if we plug in 1, we'd expect it to be at a depth of 1, which I don't think this will do. One sec, let me... Calculator, can you do logs? Sure you can. So 1, log of 1 and log of 4 is 0.6. Which means I think we need the ceiling. Yeah. So from 1 to 4, indexes 1 through 4, those should all be I can't tell what this is doing. Sorry, I'm gonna need a different calculator. This one is worthless. One sec. Okay. I have gone through and verified that I am not correct. So, turns out, if you do it like, if you use logs for this, you'll actually get an off by 1 error, and it will compound and get worse and worse over time. At least that's what my math is telling me. So log base 1 or log base 4 of 1 is 0, and log base 4 of 5 is greater than 1, which means we only get 3 nodes between our place that we can actually fill, which doesn't work for us. So if I do log base 4 of 1, that's going to come out to 0. I don't know why it didn't do it there. But if I do it of 4, okay, it's still not doing it. This was working. I swear. It's, I don't know what's going on. Anyway, point being, we can't use logs, so we're not going to. Int current depth equals 1. Int next depth is 2. Yeah. This is gross, but it will work. So we're going to start at 1, count up. When our depth is equal, if our I is equal to our next depth, then we want to take the current depth and increment that, and we want to increment our next depth by our power of 4 to the depth, current depth, which means this needs to be here. Does it? Hold on, that might be wrong. I think that's wrong. That is wrong. Cool. Good to know. So, how does this work? Very carefully. So, what's happening here is we have a current depth. That's how deep we are in our tree right now. And that's the actual depth of each node at that point. The next depth represents the index when we need to increment that depth value. So the first one is going to be 0. So when you're at 0, you increment it to 1. We already did 0. That's right there. So instead what we can do is we can actually go into it and start at 1. And so as we increment through this, we add on n plus 1, or 4 to the n plus 1th new nodes, and that's how many we have to wait until we increment. It's the exact same logic we're using here. We're just doing it here as well, which is getting a little bit, admittedly, gross, but that's not what I meant to do. But it should work, I think. So what do we need to do here? This is starting to seem like more and more of a really bad idea. Why aren't we just using recursion? Recursion seems like a much better idea at this point, doesn't it? It really does. This is going to be a mess. So yeah. Ignore me. One sec. We're going to do recursive. So we're going to recursively build our quad tree. First thing we need is a quad tree node of t-type array that's going to be our tree. We also are going to need a current position, a current size, a current index, current depth, and what else do we need? Is that it? I think that might be it. This is getting gross. Really, really gross, but it's fine. We can work with this. I think that's all we need. So, all of those struggles can go away. We can struggle completely differently now. So, here's what we're going to do. We're going to pass in information to this, which means we need to call it build. Why aren't you showing up? Oh, no return type. Sure. Since we're accessing this tree, or this array rather, we don't need to return anything. So it's just going to be a void return type. Pass in our tree, the position, the size, the depth. Oh, nope, the index first, 0, and then the depth. That seems out of order. We'll do the depth, and then the index will be the last thing. That just makes more sense to me now. So, how is this going to work? That's a really good question, because I don't know yet. So, we've built our tree. I can return it here, get rid of some compile errors. That will not work for some reason, but that's fine. It doesn't seem fine. Don't know what that is. We'll get to it. So, how this is going to work, you're going to pass in your current node, and then from there, it's going to figure out the 4 nodes that it needs to create as a response to that. So, what we need to check is if our depth is equal to this depth. If it is, we're done. We hit our leaf. Which means it's very important that we set our depth first. Otherwise, we're never going to hit this. And I'm also going to just to make sure nothing horrible happens, if you pass in a negative depth right here, this would be infinite and it would crash. So I'm going to do greater than or equal to. Actually, if you passed in just, yeah. Point being, there's cases where it could not equal. And if that's the case, you will never hit that, and you will get a very long wait and then a Unity crash. I'd like to avoid that, so we're just going to be safe about it. You can still make this take a long time. It's still recursion, but yeah. Hopefully it won't crash catastrophically. So what we have is I actually don't need this. Any of this. And the reason I don't need any of that is because I can do tree index.depth. Well, that's disappointing. I'm definitely going to do that, whether it lets me or not. So we're going to expose our depth value. Return depth. There we go. So now we can access it, which is always handy. So that's exactly what I'm going to do. Pull it out, and we're good. So this means we're just going to recursively subdivide each of our nodes, and then based on that, we can do whatever we need. So this will just be a return statement here. We're done if we hit a leaf node. Everything else, though, is going to subdivide into 4 nodes. So we just need to build those 4 nodes and then call this recursively 4 times on each of those nodes. So based on the depth, we need to know how far ahead we need to go, which is going to be a step like that. Yeah, something like that. So we start here. Our step is there. It's actually going to be equal to the tree index. Ooh, wrong type of index. Tree index.depth. And so this is just the step forward. It's going to be equal to the entire length here. And then, what else do we need? I'm missing something. I think the only other thing we need is we need our index. Is this all I need? We need our start point is going to be equal to our index times 4 plus our step. Let me walk through this and see if I got it right. So at depth of 0, we're going to get a step of, we want it to be 1, which it would be because depth of 0, that results in a step 1. Index would be 0 times 4, which is 0, plus our step, so we get 1 total, which means we start at 1 and we do 1, 2, 3, 4. Get each of those nodes. We start at 1. We have a depth of 1, which means this equals 4, and our index equals 4. So 1 times 4 is going to be equal to 4 plus 4. Is that correct? I don't think so. I get the feeling that I'm thinking about something wrong, but I don't know. Hold on, I'm gonna go draw this out. I'll be right back, because this is something I need graphics for. So I'm gonna be back there sketching. BRB. So the solution is actually identical to what you do for a heap. So to find the children indices, for a heap, the actual algorithm for that is 2i plus 1, where I is the index, and 2i plus 2. The reason there's 2's there is because it's a binary tree. We're making a quad tree, but that doesn't mean we can't use this. So we don't need any of this. Our index, our next node, is going to be equal to I, which is I is going to be our index, plus 1, and then we'll have 4 of those. So I actually don't, I'm going to leave the 1 off, and then what we're going to do is do tree, what did I call that? Next node, plus 1, and we'll do this 4 times to get, well, let me initialize this first. New Quadtree. We're going to need to actually calculate the position, which we can get to. And yeah, we'll do that next. But for now, I'm going to make 4 of these. 4. Cool. So what this is doing is 2i, it looks at the next one, so, and then you get the plus 1. That was a terrible description. Let me do better. So if you have a tree, start at roots 0. 2 times 0 is still 0. If you add 1 though, you get the next node. And so you add 2 and 3 and 4 and you get the next 4 nodes. Then if you're at position 1, you multiply that by 4. Sorry. Then you'd get 4. If you add 1 to that, you get 5, which is the first node in the second depth. And then you do that 4 more times, and you get those 4 nodes. And that works all the way down the tree, which is fantastic. So we can actually use this. Now we're building our tree. Our tree is now built. It's just not done yet. We need to actually, the next thing we need to do is actually figure out where our position is going to be. And so the way we can do that is actually to position things. So again, not really concerned with performance yet, because just the way we're building this. So this is all temporary. It's a one-time cost, so it's not super significant. So we're going to make a delta, which is going to be the change vector, and I'm going to define it something like this. We're going to take our current index, take our current size and divide that by 2 and do that again. Oops, that's not how I do that. And divide that by 2 as well. So this is going to get us half of our size. It will move us, actually, we want 1/4 of our size. Because our size represents the entire distance across our node. And so that's not quite what we want. We want to get a 1/4 of the way across, because we're at the middle. We want to get halfway between them. Can't do much there, but we do want to keep these similar. So our Quadtree indices we do want to kind of keep relatively similar. So we need our position. Oh, come on. Can't do that either. Got to keep looking up stuff in our previous node. So we're going to take our position minus our delta, screw it, I'm going to do a delta x and a delta y. It'll just be easier this way. If you want to make this more optimal, you probably can. But at this point, let's just get it working, and then let's figure out where to optimize it after that. So we want to get the top left, we're going to subtract our delta x and add our delta y. And that will get us our position. Our size is going to be equal to the tree, or its parent's size divided by 2. So we're reducing each dimension by 2, cutting those in half. The depth is going to be equal to the current depth plus 1. And I think there's just a default value required, which we can skip. So we've done it once, so let's just do it 3 more times. Gonna modify the formatting a bit just to get it nicer. But then just copy and paste. And then if I remember, it goes top left, top right, bottom left, bottom right. Cool. So this was just a subtraction. This is addition, subtraction, and addition. Cool. So that should all work now. So the only other thing we need to do is to build the quad tree recursively on each of those nodes. So we can pass in our tree and next node plus 1 and so forth. And that should actually build it, the whole thing. It should build our tree. So unless I'm insane, it's done now. And I can actually drop pretty much everything. We just need to pass in our 0 index. Everything else is fine. And then we just go until we hit maximum depth. So yeah, there we go. Our tree should now be built. So all we have to do is actually implement everything else. So I'm going to delete the old insert. We only use that in our pen anyway, so I'm going to drop it for now and then fix up our circle insert. That should work now. And then our circle subdivide is now a circle search, which will keep it. Probably should have just done a refactor there. Oh well. So we get there. What we're going to do is we could do a search actually, but we're gonna try to keep our logic the same. What this is doing is this is actually subdividing here. We don't need to do that. We don't need to subdivide our subdivided tree. That's just way too much. And I'm going to remove our should reduce as well. So that all goes away. Then the only thing we need to do is we have selected nodes, target position, radius, value, depth, subnodes, .length. Let me catch up on actually where we are. I may have deleted a bit too much, but I think we're fine. So we want to search each of the subtrees, which means we're going to do more recursion. Yay, I guess. So what we need to do is we can actually remove that data. I'm not going to set any data here. I'm going to do it up here and actually iterate over each of the nodes we return, not here, down wherever we do our insert here. So we're going to circle search, and then I'm going to iterate over those leaf nodes and actually update them inside of here. This way we just have a way to search. We don't have to do anything else. So we add last, what? Oh, and then we add the current one. Got it. So we don't want to do that. Instead, we're going to want a, this is going to get really long, Quadtree node of our t-type with, and that'll just pass in our tree. And then we want an index. Now, we're not going to keep it like this. This is gross. But for now, again, we're just getting this in. We're getting a rough sketch of kind of what we want. And then we can go and slam it down and get rid of everything we don't need. Okay, so now that we're here, what we need to do is pass in, we're passing in a position. that we're targeting, but this was supposed to be inside of a node. So we are going to actually need to pass in a Quadtree node now. So we can now search over that node's position and the node size and so forth. Why can't I access your position? It's kind of weird. Okay, I think IntelliSense is just broken there. That's fine. So, battery exhausted. This is going swimmingly so well. Sorry about that. My camera died. So, this video hasn't gone smoothly. Currently, I've been recording for about 2.5 hours, and we're still not done. I think there's going to be a lot of cuts here, mostly just because a lot of those are a lot of the time I've been spending. I'm getting over a cough and, well, cold or something. I'm getting over something. That's a better word for it. And it makes talking for a long time difficult. So we're going to finish this. Hopefully the camera has enough battery to actually do that. I didn't check. That would have been smart, but I think we're almost done. Famous last words. So what we need to do is this circle search is going to recursively search down through our tree. To do that, we can actually just use this next node we have here and just do it 4 times. So from 1 to 4. So what we need to do is check if those nodes are contained in the circle, and if they are, then we need to do something about that, which is going to be take our tree, pass in the next node, plus I, which is going to be our offset. And so that's not what I wanted to do. Wanted to do that. That's the node we want. So we want to look up that node in our tree. There we go. Getting there. Going weirdly, but we're getting there. So what this is going to do, it's the same thing as up here. Only difference is instead of doing them each individually, we wrote a for loop. That's literally it. So we're going to do the same thing, except now we need to recursively call here. So we're going to do our tree and then our next node plus I, which is our same index. So we're just incrementing the index, passing in the tree, and continuing along. We also need to pass in the depth. We actually don't need to pass in the depth. Again, for the same reasons. So we don't need the depth and we don't need the value. So I'm going to actually just pull those out because we don't need those. Those are both coming along from we can find those. So instead we want to see if this dot depth is equal to our tree index dot depth. If they're the same, greater than or equal to the same, then we're done. And then we just add our tree index to our selected nodes. And that will just return back all of them. And we just do a recursive call on this. Tree, next node I. Cool, that's all good. Circle subdivide is unresolvable. That's because we renamed it. Circle search. This is why you always refactor, because it catches those. That is fine. Then there's just 2 things. Well, this can go away. 3 things. 4 things. Sorry, it keeps getting bigger. Nodes, we're going to start at index 0. We're going to start at our root and trickle down. Building our quad tree. position, size, depth. Why doesn't it like that? I don't really understand. And it doesn't seem related to the read-only call. We'd get a different error anyway. I'm just gonna leave that and pretend like it's fine. That's usually a good way to solve problems. Just ignore them. So that leaves us with one thing we need to implement, which is our get leaf nodes, which actually is going to be hopefully simple. So what we can do is, based on our depth, we know we are going to have 4 to whatever power. Battery exhausted. So my camera died again. Sorry about that. I need a replacement battery or something that can keep it charged while I'm recording. Clearly, that's not working. So I've turned it off. Sorry about that. Or you're welcome, I guess. If you don't, I know some people don't like the face cam. So what we're going to be doing with this enumerable get leaf nodes, we need to calculate the total number of leaf nodes, because we're just drawing those leaf nodes. Is anything actually using this? Before we actually spend all this time on this, if I remember correctly, our quad mesh creator is using it. It is. And I believe our something else is using it. Quadtree component? Something like that. Yeah, that's doing something else. So we can ignore that. We'll take that gizmo out for now. We don't care about that. So our Quadtree mesh creator is taking every leaf node and building a mesh from it. We can use that. So leaf nodes, this is going to be equal to our our math pow of 4 to our depth. So this is going to take the depth of here, where is it? This guy, our Quadtree. Something weird is going on. Why? Oh, I have too many. Got it. I had too many brackets. Got it. Cool. Solved. So we're returning an enumerable list of Quadtree nodes. So we can actually use a really simple yield statement for this. And we can start at our nodes.length minus the leaf nodes. Oh, that's not how I want to do it. I equals that. And so what this is going to do is we're going to start at the beginning of our leaf nodes, which is going to be, they're going to be at the end of our array, and there's going to be leaf nodes number of them. So if we take the end of our array and step back that many, that's going to be the start of the array, or the start of our leaf nodes. So what we want to do is we want to return the subarray that has just those elements from there to the end. And we can do that using our yield return of our nodes I. And so this is just like the yield we were using previously, except now we're just doing it here instead of further up in our actual Quadtree node class. So, does it actually work? Do we have a bunch of errors? Quadtree component is broken, Quadtree pencil is broken. That's fine, because I don't care about you. You can go away. We'll fix that later. We can actually fix it now. We can just change it to use the circle. That'd be fine. But I'm also going to take out the gizmo for now because it's not going to show much useful information, and we just can iterate over everything now. We can just iterate over the array, which I can write myself. There's nothing particularly interesting going on there. That's broke. So we have our Quadtree mesh creator throwing a ton of exceptions at line 67. Our leaf nodes are throwing errors. What is going on? Oh no. It was supposed to work. I'm gonna disable the automatic, there we go. Array index out of range. So we may have done something silly and not made it big enough. I think we may be off by 1. And we'd be off by 1 here, if I'm correct. So I less than or equal to the depth. This will actually create it so it has our correct depth. Did you actually? There we go. So if we restart this now, it should work. And if I regenerate it, it may take a bit longer than a bit. Well, that's interesting. Oh, duh, I know what's going on. Everything's working, except the one thing we need to work. Our insert creates this leaf nodes. We need to actually leaf nodes.for each. There we go. For each Quadtree node, set the data equal to the value. Ta-da! Maybe a value type, so I don't think we can edit it. That was short-sighted on my part. How can we make this work? I think if we restrict our T type to a object, class, maybe. Okay, hold on. We'll get there eventually. There we go. No, that's still not going to work. Shoot. So the trouble we're running into is caused by our struct here. If I make this a class, whoa. There we go. If I make it a class, that error goes away because we have, again, we're using value types. We're editing the value type, which breaks it. So we can't really do that. Let me use just classes, and we should get something better going on here. Or not. What? I didn't anticipate this taking so long. So we've built our node, doing a bunch of recursion, doing all of that. I'm going to put a breakpoint there and there, attach to Unity, and then start. And hit this. How many objects are in our leaf nodes? 1. There's only 1. What the heck? Why are we only getting 1 thing here? Unless I'm incorrectly placing things. Let me do something really bad, and then we'll see what's going on. Public Quadtree node dtype array nodes. We're gonna just return those because why not? And break a bunch of stuff because ReSharper isn't listening to my settings. And now we should be able to get this in here. So I'm gonna uncomment this. And we don't need most of this. If Quadtree is not null, then for each node in Quadtree.nodes, yeah, for each node in our nodes, do a draw node, maybe? Sure, draw node. I will pass in the node and the node.depth. So why do we need that? We can just pass that there. Done. Cool. Awesome. Works. We can get rid of this. That's all good. Do the node. Set the depth. Ta-da! Okay. So that should draw our tree. Unless I'm insane. And it does. So I'm wondering why we're inserting nothing. This is the wrong project. There we go. Because that doesn't make sense to me that we would not insert anything. That seems very wrong. And we should fix that. But how do we fix it? Okay, I'm going to attach to Unity one more time. We get leaf nodes, that should be fine. What's our value? 1? Cool. But why did we only find one thing? That doesn't make any sense. Grr. We're gonna subtract 1 from their depth. This is I think this doesn't make sense to me in my head. But just to make sure it's not an off by 1 error, we're going to try that. Okay, something funky's broken. And it's not that. Well, might be that. But I'm going to pretend like it isn't. So, we insert all of our stuff. And it all supposedly works. Do I just need to make it bigger? Maybe that would help. I don't think it would, but you know, never hurts. So we are getting a bunch of deletes and inserts, which is good. That's what we expect. But none of it's actually doing anything. So one more test, just to make sure. Totally not insane. What is your position? Zero, 0. That isn't right. So that's our problem. Well, no, hold on. Depth of 0, size of 8. Hold on. We fixed that. The depth is set. What is going on? So it shouldn't be returning. Oh. I found it. This is backwards. So our tree depth has to be greater than or equal to this depth. not the other way around. The other way around is wrong. That's why we were only getting our... There we go. That took way longer than it should have. But it works now. Everything is back where it was. Yay. Oh, that took forever. But it does work. We can insert, we can delete. And everything seems to be good. Colors still, or the different values still work. So this works. Good. We got an array, which means that next time we can actually do marching squares. Which hopefully that isn't going to take as long as this did. It probably will take longer. Mostly because that isn't, the algorithm is going to take a little bit of tweaking. There's 16 combinations, if I'm remembering off the top of my head, that we need to implement. So we'll have to handle all of that in our mesh generator, which means we'll be generating a separate mesh creator that will generate based off of marching squares. But once that's done, we will have sort of a smooth-ish mesh going on, and then we can actually optimize it and join some of these vertices that are currently being very much duplicated. And then we can add some cool shader techniques to smooth these things out a little bit more and actually fade between these. So that should all be coming up soon. But if there's anything you guys want to see, I'm always curious to see hear what you guys have or suggestions you guys have. So far they've been pretty interesting. This is a suggestion from somebody, so yeah. If there's anything you guys want me to change, like my batteries for my camera, then let me know about that too, because that's sort of how I get better and better at this, is I figure out what works and what doesn't, and when you guys actually tell me, it makes that process a lot better. So don't hold back. You won't hurt my feelings. Well, you might hurt my feelings, but that's fine. So yeah, that's it for now. So until next time, see you, internet.